So this is the past paper. You can see since I'm sharing the screen, and you can also download a copy. I uploaded this particular PDF and also the relevant data set into the LMS. So you can download it from there as well. If there's a data set required for the third part, so those things can be found there. So you can download it and continue work on it and let me know the answers once you have it. Now I might pause this recording for a few minutes because until you are doing, otherwise it will be a complete blank. I will be just staring at the camera. Okay. So when you have something to discuss or when we are discussing the answers, I will resume. If I forget, please remind me in the chat. So the first part of the question is from the very basic one. It is asking why there are two computing types called soft computing and hard computing, and what things or what attributes we can use to determine which computing we use. So if you remember at the first day, I showed you a slide like this. At the beginning, I told you there are certain places where computers are used and certain places where computers are not used. And these are some of the scenarios that divide, these are some of the facts that divide these two categories. Sometimes you have very precise data, sometimes you don't have precise data. Sometimes rules are known, sometimes rules are not known. And also the computational complexity is again an issue. For example, if you look something like a calculator, then all the data is known. So you can use hard computing. However, if you look at something like playing a game, like the game I showed you in the Dota 2, there all the information is not there. You have no idea where the other opponents are, and you don't have idea their health and their strategies and things are not there. Therefore, you can't use hard computing for that. Similarly, if you look at something like hand signature verification, again, it's not exactly identical signatures found by the same person. There can be some distance, some differences. Therefore, in that kind of scenario, you need to use soft computing techniques. So those are some of the attributes that are required, that attributes that can be used to classify or identify which computing technique to use for different scenarios. Now the part B is an extension of the same situation. Now here you have, you are introduced to a scenario where it is related to a bank and asked what kind of computing to use for each of these cases. And you also need to justify your selection. So it can't be some random saying, okay, this would be soft computing, this would be hard computing. You have to justify why you had chosen that particular computing type. For example, a bank is converting its manual facilities to automated, and you are asked to specify which of them would be hard computing and which of them would be soft computing. First part, calculating the net interest of the saving account. Which one do you think is the best computing method, hard computing or soft computing? Calculating the net interest? It would be hard computing. Why? Yes, data is very clear and very precise. And we also know the rules quite well. How about this one? Counting the total number of customers served in a given day. Instead of counting, let's say, number of people who interact with the bank on that given day. Interact in the sense, uh, deposit some money, took some cash, or something like that. How many people interact with the bank on a given day? So which method should you use? Yes, because when you do a transaction, that data is recorded in the banking system. So you can do some kind of database query and get the number of people. Uh, what about this one? Third one, face recognition of customers for security reasons. Sometimes you have it. When you are just entering the bank, the moment you enter the bank people know who had entered, and whether it's a known customer, whether it's a thief, all these details are displayed. Someone says soft computing. Now I need the justification as well. If you're saying soft computing, you have to tell why you think soft computing is better. What's the reason you have chosen soft computing for the face recognition? Okay. Uh, Identify the data is an image and need image. Yes, image processing, not image processing, actually it's called computer vision. It's part of the soft computing, but can you be a little bit more precise? For example, in the previous case, you said the data is very precise and accurate. Here, of course, you can say data is noisy and imprecise, but I want to be specific for this particular scenario. When it comes to face recognition, what kind of data and information do we have? For example, is the same person look always identical at different visits to bank? Yes, because people change, right? They take a different haircut. They might wear a different clothing. And if the person just came from home, or maybe had came after a long working hours, then the appearance and things can change, right? So it's not like exact pixel to pixel kind matching that works. We should identify which are the key features. Maybe the shape of the face, maybe the place of their eyes and things like that. You need to identify, right? So they are not very precise and they can change, like the colors. If it's a lady, they might put makeup, so those colors can change, and the gent might have a beard or not. So The software need to identify those imperfects or missing facts. For example, if someone wears a sunglass, then the data about the eyes will not be there. So there will be missing data. Right? So the software need to identify those things and make some justifiable output, some justifiable guess. Right? Then we need to have soft computing. Updating the bank account when the money is deposited. If that's the easy one, right? Updating the bank account, then you should not probably give it to a neural network which might have certain probability to identify it wrong. You should go with the hard computing because everything is there. Right? The data and the rules and everything is there. So it's definitely a hard computing problem. Calculate the credit limit for new customers based on multiple factors such as age, profession, banking history, etc. Now, I don't know how many of you are using credit cards. So the credit limit is not actually fixed. You might think, okay, everyone gets 30,000, 1 lakh, or 2 lakhs, or 50,000, or something like that. That's not the case. The bank manager and the people have the ability to adjust the amount depending on what they think. So sometimes the same 2% with the same profession might get two different credit limits because they will ask different questions, whether they had any other accounts in other banks, whether they had any previous credit faults or things like that. So depending on that, they might have different opinions and give you different credit limits. Right? So the idea of the credit limit is to give a credit limit where the person is able to pay. Otherwise, bank will be in trouble because the person will not be able to pay the amount. Right? So as the question says, this was done in manually. Now it wants to. Now the bank want to automate it, right? So the bank will. So the software will get many details like the profession, the banking history, and things like that. And it need to make a decision on what is the credit limit to offer for a customer. So is this a soft computing problem or a hard computing problem? And why? Right? Now the chat is already coming up soft, hard, soft, hard. I need the information as well. I need to justify. Remember, the question says answer and write a very brief justification, at least 2 to 4 sentences for your decision. Now, I don't want to have sentence, at least in the bullet form. You should say why you think it's good for soft computing. Soft computing because there are different input parameters to consider, which may have different contribution to the outcome. Yes, that's a good answer. The data can be having so much variation. Yes, that's again a possible scenario. Means the data can be some, you can think about in all the three categories. For example, data can be sometimes false. The person might say something wrong about intention, unintention about his past data. And data might be missing for certain facts. And it may not be precise. For example, some questions can be answered as good, bad, sometimes, not with numbers. Right? So in that case, you can't plug it into a formula. And the rules are again not well known. For example, it doesn't say people who are doing this particular job will always pay the credit amount, or the people who are living in this area are good people, so they will do they will always pay the credit on time, or this person, uh, things like that are not there. It's not a very precise set of instructions. It's a combination of all the things that can create a sort of like a uh, case or a person's character. So you have to look at all these things before making a decision. And how you combine these different factors are not a very standard way. It depends. Therefore, soft computing needs to be used for that one. Uh, let's move to the ninth one. Calculating the total income of past 6 months. So this is this bank want to know how much it had earned in the past 6 months. So what about that one? Total income of the bank in the last 6 months. Hard computing. Data is clear. The next question, estimating the income for the next 6 months. Soft computing, yes, because it needs to analyze the trends. Right? Analyze the trends, and so the data is not known, so you have to predict values. So for predicting and things like that, soft computing is needed. We'll move to the second question. Name three different architectures of neural networks. So there are different designs, right? Depending on how the neurons are connected, you have different types of neural networks. Can you enable? Can you name three different types? Free code, yes, that's a easy one, the one we had been learning. What about two more? Recurrent networks, yes. Radial bias, okay. Anything else? Radial bias is duplicated twice. You have two feed forward and right. You have to. Okay, I forgot about the recurrent method. Right. Let's move to the part B. Write a MATLAB script to calculate the output y of the neural network displayed below. Weights are displayed within the parentheses. Bias is always +1. You do not need to code the weight updating component. Transfer function is linear. I'm not sure if you can view the full image from this one. So if you're having problem reading the document, you can download it from the LMS. LMS, you have this PDF. Yes, I have to zoom it because the problem breaks across 2 pages. So try to calculate the output. Now, 3 inputs are here. 3 inputs are here. X naught is the bias. You can see X naught mark in here and here and here. And weights are included in the parentheses. You are asked to calculate the output Y. You can write a MATLAB code if you want. I think that would be easier rather than doing it manually using a calculator. So try to do this second question as well. And you need to find the output for each of these inputs. What will be the output for each of these cases? Okay, give it a try. So the third question is, you are provided the certain data sets. Okay. So this is a type of shellfish known as abalone. And depending on that, you have to calculate how much meat is inside each of these abalone. Okay. So following data is provided. Its sex, length, diameter, height, whole weight, shark weight, and some other features are there. And what you need to do is you need to predict the age of this abalone. Right? You need to calculate the age of the abalone. Right? Now, age of the abalone is given by the following formula. Age is number of rings plus 1.5 in 1.5 in years. Right? So we'll start with predicting the values. Okay? So what you need to do is you have to set download the data. We'll start with that one. So start downloading the data set and open the MATLAB, and we'll see how we can work on this particular question. I will upload the data file to the chat as well, so anyone who doesn't have access can download it. So the fact is this. I think I need to explain the question a little bit further. So the counting the number of rings in the abalone is hard. Because you have to cut the abalone and count it inside. The rings are not the ones that you see here. Okay. So the idea is, okay, measuring the age is important, and the conventional way to get the weight is by counting the rings. You count the number of rings and add 1.5, and you get the age in years. It's just like in rings in the trees, right? In a tree, you know that you have a ring when you cut the timber, and each year you get a new ring. Similarly, this particular shellfish create rings. So if you want to estimate the age of this shellfish, you need to count the number of rings and add 1.5, and you get the age. However, doing that is a bit hard. But there are other parameters like this which can be used to estimate the number of rings. So if you know the number of rings, then you can estimate the age as well. So what the question basically says is, create a neural network So when these details are provided, it estimates the number of frames or the age. So that is the overall idea of the question. So the first part is copy the data set to your answer and use Excel to do the bit of pre-processing. And these are the things you need to do. You need to separate the columns and rows because it will be in a CSV file, if I remember, comma separate values. Then you need to process the data. For example, this one has male, female, and infant. Right? So it's in a categorization of data, not in a number. So you need to somehow put it into numbers. And then the rest of is the ones that you have done early. Create a neural network, train it, test it, and finally do the post-processing. So you can get the age of the epsilon. So if you predict the number of rings, then you have to do this little bit of post-processing to get the final age. So that's the question. So start by downloading the data and importing it to Excel. After that, doing the bit of pre-processing. When you complete, maybe you can send the Excel sheet so you can check whether it is okay or if there are any things that you would like to change. Right? So the steps are as follows. You import the data, then you convert all the textual data into numerical data. Since there were three classes, we follow this particular pattern, not 0, 1, 2, this particular pattern. Then we imported the data into the MATLAB. Then we import the data into the MATLAB. Okay. Then we load the data. And then you need to make sure the data set is either already randomized, or you have to randomize the data. Then make sure it's in the correct format. That means samples are in separate columns. But in this data, it's in the other way around. Samples are in different rows. So you do a transpose. So everything is in the correct order. You separate the training and testing data set, maybe 20 to 80 kind of ratio. You create a neural network using new feed forward net command. You can decide on how much neurons you are going to use. Do a training and a testing. And after that, you can do a post-processing as well. Because our idea is to predict the number of frames. If you can predict the number of frames, then you can calculate the age. So that is the simple discussion of how to do this particular question. Anything you want to ask about this question? Anything related to this past paper you want to ask? Okay. If it is clear, that is good because that's all you have in the last year's paper. I think this last year paper was a little bit too easy. You better take the standard difficulty as the year before that. Last year one, I feel like it's a little bit easy, especially the first question. Okay. If it is fine with you, I'll just cover one single last topic because this is the last day, I believe. And then I'll let you ask any other question related to the full course. Now, so far we have been working with the feed-forward networks. We dive into a little bit of different type when we said deep learning network, and we did a little bit of training on the deep learning as well. But yes, hello. Hello. Okay, so we had learned a little bit about deep learning, but still the same kind of structure was there. So I thought I will show you this small example on how to do a different kind of neural network. Now this is known as a self-organization map. So this belongs to a different type because this does not have a
So I think
supervised
this
learning.
today is not the last day. Hello?
Hello, yes, Janak, tell me.
Hello?
Hello, yes, I can hear you.
So the thing is today is I think not the last session. Next week also
Maybe we have another one after the next week.
hello.
Let me check because I'm doing about 3 more courses. For the morning one that started parallel to you, this was the last day. Let me check. So I thought everything started in the same date and finished on the same day. Yeah. So why are we replacing the text by numbers? Why is 101 instead of 2-digit combinations like 0001 or 11? The fact is, if you use 2 digits like 00 or 11, there is a possibility you might be giving it the wrong set of data. For example, if you look at 00 and 01, they are two different classes. Right? But the first input is 0 for the both. Right? And so that means the first input sort of like should be same for the both first class and the second class. And the second digit that you are sharing is with the second class and the third class because you are using 01 for the second class, 11 for the third class. So if you look at the second class in the middle, it doesn't have a sort of like its uh, independent kind of value because first digit it need to share with the first class. So anything that is related to the first class will affect the first input from the first class and the second class. And the second input will be affected by the second class and the third class. So you have a little issue there because neural network will find it a little bit hard. You have to do a extra processing to get that combination as well. Because you have to now look at the both digits together to identify which class it is. Because input, one of the input to your neural network is what class it is, whether it's class A, class B, or class C. Now the neural network some extra work to do because it can't identify the class directly. It can't identify whether it is class A or B just by looking at a single input. It had to look at the first input and the second input and find the combination. If it is 00, that's one class. If it is 01, that's a different class. Similarly, if it wants to know whether it's a second class, the input is whether it's from the class B, again it had to look at the both inputs, 0 and 1, first digit and the second digit. So you have some extra processing to do. Right? It needs to identify both of these digits and find the pattern itself. So it knows 01 means a different class, 11 means a different class, and 00 means a different class. So you need to do another pattern matching just to identify that particular class. So we don't need to make it any harder for the neural network than it is already. So if you use something like 010, now if you look at the pattern, it's not a random pattern. Each class has, or in other words, if you have 5 classes, you have 5 bits. So the number of bits is equal to number of classes. And let's say you have classes A, B, C, D. Then the class A will have first bit as 1 and all the other bits as 0. Class B will have second bit as 1 and all the other bits as 0. Similarly like that. So if you see class C, if you want class C, then only the third bit will be 1, other bits are 0. So neural network only have to look at the third bit to know whether it is class C or if it is not class C. It doesn't have to find other patterns just to see what kind of number or what kind of class it is. Just by looking at a single bit, it can determine whether it belongs to a certain class or whether it doesn't belong to a certain class. It's almost like the one we did in the last time when we had three iris flower classifications. We use this kind of notation, so it's the same scenario that we are using here. Right. Now let's go back to our code. Right. Now the difference in this one is we will be using unsupervised training. So far we have been learning about supervised training. That means we provide the neural network with the training, that means the target as well. We provide it with the sample answer, but that's not the case. We'll start with this one. First, let me comment on this one. First, we shall load our data set. Okay, so you can follow the program with me. First, we load the data set, and you can see this is the data set. And here, you can see it only has the inputs. It doesn't has the category. I hope you remember this one. This is the iris dataset, so you already should be familiar with this one. These are the sepal length, sepal width, petal height, and petal width. And after that, you had the flower type, but that data is not here. We only have the measurements or the inputs. Right? You can see all the 150 data is here, but not. I do not have any categorization. Then we are going to create what is known as a self-organizing map or a Karnaugh map. Sorry, self-organization map. So in the self-organization map, what you do is you basically take a data set with multiple dimensions and try to reduce into two-dimensional plane. So what do you mean by multiple dimension? Dimension means the number of attributes you input into your neural network. So in this case, we have 4 attributes. 1, 2, 3, 4. Petal length, petal width, sepal length, and sepal width. So they have 4 dimensions. And if you look at something like an image, it might have even more dimensions. If you go pixel wise, you might have even more dimensions. If you look at the previous one of the shellfish example, I think it had about 10 or 12 different attributes. So that's a large number of dimensions. So what the self-organization map does is it tries to map all this data into a two-dimensional map. So we can visually see how each of these attributes are related. And sometimes you are able to group them or classify them just by looking at it. Okay. Now remember, you can't do a two-dimensional plot directly on four-dimensional data. If you only have the X and Y or some kind of data, you can do a two-dimensional graph. If you have X, Y, and Z, maybe you can do it with the support of a color or a height or something like that. But when you have about 4 different attributes, it's hard for you to plot this in a 2D plane. So what the self-organization map does is, it tries to map this into a 2D plane. So the command to create the self-organization map is self-organization org map. After that, you can give the size of your self-organization map. That is number of rows and number of columns. So I arbitrarily choose 5 and 5. You can choose whatever you like. Let's say 6 and 6. So it will create a 2D map of 6 by 6. You can think of it more or less like a okay, we'll see the preview, so you can see it. Okay, so you create a self-organization map of 6 by 6. Are you following up to this point? Okay. This second one is optional. If you want to change the number of training parameters or any other parameters, you can use them. It's quite similar to the ones that we have used in feed-forward network. But for the time being, we'll go with the default one. Default one is around 200 records. Then we'll use the train command. Now, if you look carefully, this train command has only two input parameters. In the neural network train command, you have the network name. So net is my network name. And you had the input. And then after that, you put a comma and you input the targets. But here we don't have a target. The reason is this is a unsupervised learning. That means the network itself tries to learn the pattern. It basically tries to group similar things into similar groups. Okay? So you don't have a target. You are not giving it any correct answers. It just gives you the question and asks you to do a classification. Okay? Let me first run only the first two lines so we can see the attribute. You can see there's the neural network appearing. Okay? So this is the network. Now, if you run the train command, you will see, sorry, you will notice this train window, quite similar to the feed-forward neural network. You have the network structure, the design here, the input 4 dimensions. We have 36 elements, 6 by 6, and the output is 36 because it's like a grid, 6 by 6 grid, and 200 epochs. And if you click this sum topology, this is how the network looks like. So although I said it's 6 by 6 grid, it's more like hexagonal because you need to have the internal connections. So if you want to know about how the neighbors are connected, then click the next button. So this is how the neighbors are connected. So each of these neurons has a weight. Sorry, each of these interconnections has a certain weight connecting them. Now let me show you the third graph. By pressing the third one, you can get the third one. This one is known as neighbor weight distances. So what does it mean? Now remember, it tries to map our sample data into different classes. So what it happens is there are 36 possible places to put. So it tries to map each of them into some of the places. And the ones that are in light colors basically shows classes that are very closely related to each other. So they have similar attributes. Right? They have similar attributes, maybe the similar sizes, similar length or things like that. So if you look carefully, there are two data points here and they look very closely related because you can see it's a very light color. But there's a dark line going across this one. So that means whatever the sample here and whatever the sample here are quite different. There's a large difference. But between these two samples, there's a similarity. So we have a group of flowers classified here. They are quite similar. So most probably they belong to the same class. And there's a dark line separating the data set. So that means there's one flower type here, and there will be a different flower type or many flower types that are different to the first flower type in this region. You can think of it like a fence. So some of the flowers are in this side of the fence, other flowers are in the other side of the fence. So you can very clearly see there are at least two different flower types are there. One flower type is here, and other flower types are on this side. There is a gap in between. So there's a very large difference, discrepancy between these other samples. There's a large difference. We can look at how the samples are distributed by going to the next one. So if you look, click the sample hits or sample histogram file button, you can see this is how the actual file data samples are distributed. So 12 means 12 samples are closely attributed to each other and they were put into this particular cell. And there's another sample, another 10 samples here and another sample is here. And you can see they are very closely related to each other. So there's most probably all these samples belong to the same category. And there's a white line going here. So that means there are no samples in this particular line. So either you have parameters close to this class or either you have parameters close to this class. There are no flowers that are in between. Right? Maybe this flower is tall, maybe this flower is short. There are no flowers that are in between the medium height. There are no exist. Right? So like that you can see there's a difference in the class. And you have one set of attributes here. And you can see there are some large clusters here. So what you see here is two different flower types that were linearly separable. If you remember in the iris dataset, two flower types were linearly separable, other two were not. So what you clearly see is the two different flower types that were linearly separable. So probably this one has two different flower types inside it, but it's hard to discriminate because they are not linearly separable. But these two flower types and this third flower types are quite different and they can be linearly separated. So you can simply assume a line and see they are sort of like different. Right? And this is how our samples and weights are distributed. If you look at the input planes, there's another button called input planes, which basically describe how flowers are categorized based on the different inputs. Now there are 4 inputs. You can see there are different ways. For example, in the 4th input, you can see this one is dark and this side is light. So it's most likely there are 2 classes. And the 3rd input again show the same pattern. So maybe this is the petal length and petal width. So by looking at this, we can say, okay, petal length and petal width are quite related to each other because they seem to be similar classes, seem to have the similar length and similar width, right? So because these two patterns quite like each other. So most likely they are interrelated. And we can see it's quite, you can see the difference between the two classes. This side is dark, this side is light, this side is dark, this side is light. So probably there are still 2 different flower types, one in this region, another in this region. Right? You can separate it either using the 4th input, that means a flower length or width or something, or the 3rd input, that's again possible. However, first 2 inputs may be the sepal length or sepal width. I can't remember the exact input. It's a bit hard to classify those 2 flower types using them, especially the first one. You can see it's not like that, but you can see a different kind of classification in here. There's something happening in this region and something happening in this region. So probably there are 2 other flower types which has different inputs. We need different inputs to classify them. Not the input 3 or 4, but input 1 could be used to classify it in a different way. So that's how you can use the neural network self-organization map to do some quick mapping of the classes. So this can be used to reduce the number of dimensions. So instead of using 4D data, you can use this to reduce the number of dimension and also to have a quick view whether they are quickly understandable classes, something like that. Remember this one, we did not input the number of classes. The neural network itself found out how many classes are there and did the classification. Now, of course, you can change the number of neurons and see whether it does better. Now, if you look at this sample, you can clearly see there's a same class separating here. But after that, you have some more features here, fours and twos and ones here, and fours and twos and ones at this region as well. But there is some connection, but not in the connection. There are some intermediate values as well. There are one samples all over here, but there is a sort of like cluster. You have fours, threes, twos, and threes like that. And here again, you have 4 and 2 and things like that. But in middle, it drops to single samples. Okay? So probably this is the third, and this is the non-linearly separable two classes that are shown here. Right? And if you want to know a little bit more about self-organization map, I suggest you to go through the Wikipedia. It has some nice animation explaining how these things are done. So I think we can wind up the today's lecture. So next week will be our last one. It's my mistake. I thought this week was our last one. So what do you want to discuss in the next